Welcome back to Advent of Code 2015, day 24. It hangs in the balance. It's Christmas Eve and Santa is loading up the sleigh for this year's deliveries. However, there's a small problem. He can't get the sleigh to balance. If it isn't balanced, he can't defy physics and nobody gets presents this year. No pressure. Santa has provided you a list of the weights of every package he needs to fit on the sleigh. The packages need to be split into 3 groups exactly the same weight, and every package has to fit. The first group goes in the passenger compartment of the sleigh, and the second and third go in containers on either side. Only when all 3 groups weigh exactly the same amount will the sleigh be able to fly. Defying group physics has rules, you know? Of course, that's not the only problem. The first group, the one going in the passenger compartment, needs as few packages as possible, so that Santa has some leg room left over. It doesn't matter how many packages are in either of the other 2 groups, so long as all the groups weigh the same. So the passenger compartment one needs as few packages as possible. Furthermore, Santa tells you if there are multiple ways to arrange the packages such that the fewest possible are in the first group, you need to choose the way where the first group has the smallest quantum entanglement to reduce the chance of any complications. The quantum entanglement of a group of packages is the product of their weights. That is the value you get when you multiply their weights together. Only consider quantum entanglement if the first group has the fewest possible number of packages in it and all groups weigh the same amount. For example, suppose you have 10 packages with weights 1 through 5 and 7 through 11. For this situation, some of the unique first groups, their quantum entanglements and the way to divide the remaining packages are as follows. Group 1, 2, 3, and then we have 11, 9 with a quantum entanglement of 99, so 9 times 11, then 10, 8, 2, and these ones in group 3, and so on. For these, although 10, 9, 1 has the smallest quantum entanglement, the configuration with only 2 packages, 11 and 9 in the passenger compartment, gives Santa the most legroom and wins. In this situation, the quantum entanglement for the ideal configuration is therefore 99. Had there been 2 configurations with only 2 packages, the one with the smaller quantum entanglement would be chosen. What is the quantum entanglement of the first group of the packages in the ideal configuration? So these are the numbers for real input. Let's practice with these ones as well. So input is 1 through 5 plus 7 through 11. And then, so we kind of know that there needs to be 3 groups with the same weight. The first group, so the first group needs to be smaller, so the first group has less or equal the amount of elements as the other groups. So size, input size is this. So if I have 10, I think I know that the first one, max first size, is divided by 3, right? looking at these examples. The first group, the one going in the passenger, needs as few packages as possible. In this scenario we have 5 here, so this would be the first group. That's kind of the same first group as this, and this would be in the back. Kind of weird list of examples. Need as few packages as possible, because we need to calculate the quantum entanglement on the first group, which has as few packages as possible. So we can get the first group, because if we have 10, we can have a group with 3 elements, with 4 and 4, with 3 and 4 and 3. And if we have 4 here, this is 6, this is 10. We are, so if we have 4 in the beginning, then we have a contradiction. This can't be the first group, because the first group has to have less elements than few packages possible. Yeah. We want the ones with the smallest amount. And another thing we know is the sum. So the sum is this. So if I have group size, it needs to be this. Group weight, because each group has to have the same weight. So it has to be exactly 20 in this scenario, because we have 60, so we have to divide in 20. So we know 2 things. We know the maximum number of first, and then the weight. And we only care about, kind of only care about the first group. So we need to go into input. We need the combinations of all the subgroups. Let's say we have a list. We need to return a list of int, and each list in this list is a combination of elements from this list, and there can maximally be this amounts in it. We could try. Now let's figure out how to do the combinations. Let's say I put an int here. So I have combinations 1 equals combinations of my input with 1. So all length 1 combinations. And that'll be easy, we'll just P. Input list of it. Oh. Combinations 2. So this is where it gets interesting. So I have do the same thing, kind of true. Let's just say input.map list of it. It's again current list. List of int, which starts as an empty list, I guess. And then for each list, I do list plus elt and I kind of do something like if n equals 0, input corpus next n minus 1. Just at the end. Okay. See if this works. So if n is 0, we just get, okay, this didn't work. If n is 0, we return an empty list, right? Makes sense. If n is 1, we say next is the current ones. Maybe it should be list of. The current one is an empty list, and I take each element I have the empty list, and then I have a list with 1, 2 to 11. And again, then I have 1, 1, 1, 2. But I can't add that if it's already in the list. It not in list. 1, 2, 1, 3, and so on. Then I have 2, 1, 2, 3. I mean, bunch of duplicates here. How can I make it? Well, first of all, everything can be a set, right? Set of set. Set of set. 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 And then we could order it. Then I still go through a lot of examples, which is not ideal, but the end result is at least unique. I don't need combinations 1. I actually know now how to do max first size. Then it's just max first size. And I only want actually group weight, right? And I can filter it dot sum. Filter it after the fact. Build all of them. Only take the ones that have the sum is the group weight, and then I just check fold x, y syntax issues. That's not it. What is it complaining about? Fold 1. Start with 1, and each element from the list is added here. Initial is R, yeah, and then RT to R. So we take R is 1 times the first element. Well, R is 1, and then we have the first element, and then we times them, and then we have whatever that is times the second element, whatever that is times the third element, and this is the combination. The quantum entanglements. we get 88. Strange. We got 99 and 88 and 90. And what is the group that has it? Combination. QE. The group at 88 is 1, 8, and 11. Ah, okay, that has a smaller entanglement. But we prioritize the one that has the smallest weight, right? So we can have a map into a list of int. Oops. Okay, we go through each combination, get the entanglement, we get the entanglement. We add it to the list of entanglements that, based on its length, and then we just say, hey, what's the keys minimum key? Then we go there to the min key. Then the minimum value. Then we get an exception. Not in if we have it, then wait, we don't even need to do that. We do this. we have a key, then we can add it, else we just create a new list. I don't know how to make this in a nicer way. Anyway, so now the min key size is 2 and we get 99. So let's try with read example. Input is this. Everything's different. Input size 28. We have 9. We have group weight of 8. Group weight of 5, 16. We have a bunch of combinations probably that take a while to build. Is that it? Yeah, because we would have seen some stuff happening here otherwise. So this is too slow. I can probably add the group weight here and say probably too big. I wonder if we get a result with smaller. Say 7. Still too big. I think it's just it has to go through too many steps here. 5 is not enough. Another thing we could do is only add sorted? Yeah. Only at increasing. Or decreasing elements. Then we don't have to sort it. Let's try this. Now wait, not empty, or is that it? Yes, Lee is empty is the one we want. Because we want to get over that first bump of having an empty list. As soon as we have elements, we only add smaller ones. We have 11, 9, which is, I mean, technically we should add 11, 10, but I think then it would be filtered out by this rule. Okay, let's try with the normal one again. Still pretty slow. Don't think I need that many though. Let's try a bit less. Seven. How else could we improve it? Must be too many results still. Let's see, how long does it take with 5? Not that long, and it finds no result. 6. Already pretty slow. Okay, that took 1 minute and it found some weird result, which means we found a result, but we need to use long. When calculating So we have a classic negative int. So we would just start folding with long. Try again. And looks like max first size 6 will get us there.
This is
Okay, so this is the quantum entanglement of the smallest group, well, the smallest quantum entanglement in a group with 6 elements in it. And that's correct. That's weird. The sleigh still isn't balancing. Ho ho ho, Santa muses to himself. I forgot the trunk. Balance the sleigh again, but this time separate the package into 4 groups. The other constraints apply. Given the example above, we have 4 groups. Of these, there are 3 that put the minimum 2 number of packages in the first group. So we just have 4 groups. I feel like that would make it easier, no? Let's see. Divided by 4, divided by 4. Ah, now we have 7 though. That kind of blocked us last time. Let's try 6 again. So yeah, we really have to find a way to improve this algorithm to get faster combinations. Ah, so even with 5 we can get a combination. Okay, so part 2 is the same as part 1, basically just with 4 groups. So what we do, we get the input And we know that the size, or the number of elements in the list of the first group, has a maximum. And because the first group has to be the smallest group, so it can maximum be input to size divided by 4. Our algorithm was too slow, so we subtract one more to run it in like 1 minute or something. We can get all the combinations of 6 elements from this list of 28 with our algorithm of combinations. And then we can filter those combinations further based on the expected group weight, because all the groups have the same weight. So we know that one group, so also the first group, has to weigh input.sum divided by 4. So we get the combinations, filter the ones that have the sum of this group weight, input.sum divided by 4. Then we calculate all the quantum entanglements. We get the quantum entanglement for the smallest quantum entanglement for the group that has the smallest elements. So min key is the size of this group, the smallest size that we added to our list of combinations that have exactly the group weight. So we get the smallest one, and then the smallest out of those smallest groups in terms of quantum entanglement. And that's it. I'll figure out how to improve combinations in case we need that again. So otherwise, that's it. Thank you. See you next time. Hey everyone, quick tip on combinations. So we always have this issue in coding puzzles like Advent of Code, that you want to have all the subsets of up to n elements from a list. Let's say a list input is 1, 2, 3, 4, 5. And I want a list with 1, a list with 2, a list with 1, 2, a list with 1, 3, and a list with 1, 2, 3, 4, 5. So all of those in between, all unique subsets. And obviously I don't want a double count. And I don't want the same element twice. And yeah, if I have 1, 2, I don't want 2, 1. This example, just unique combinations basically. So how do I get there? One nice way I found is to start with a list of mapping the input to a list of itself. So then you have a list of lists. So you basically have this list of 1, a list of 2, and so on. Then you can repeat however many times you want up to this amount of subsets you need. And what you do is you add to your list of lists based on your lists. You only use the lists that have size of the current iteration. So in the first iteration I use only look at those lists with 1 element, and then in the second I only look at those, and so on. So I only add all the list once, or I only process them once. And what I want to do is I add, based on the input, I map the input. Each element is an element in the input, so 1, 2, 3. I map this and add it to the list, and I need to restrict that by filtering in some way. So I can either do the current element, I only consider elements that are greater than the largest, or I only consider elements that are smaller than the smallest. But yeah, let's stick with this, and yeah, that's how you can get the list of lists of possible combinations of a list. And yeah, that's it. One thing we can try is what happens if we do it with letters. And yeah, similar. We works the same. We get, because we can compare the letters, which one's bigger or smaller. Oh, compare strings, we have the same filter criterion and we have the same criterion on lists as well. Then the last thing we can do is, what if we only want elements up to of size n, like I could do filter size equals 4 or something, then I go through the same process and build it. Alternatively, I can reassign. So if I change this to var mutable list, I can reassign it. Okay, there's some kind of issue with the iteration, I think. Nope, that doesn't work. +1. But I don't want 5, I want 4. Okay. Yeah, I think the iteration starts at 0. 0 indexed. So I start with the list of all the ones, then I go through it and always replace the combinations and only look at the list. And then I get, by replacing, a more efficient solution to only having sublists of my list with 4 elements. That's it. See you later.